Alright, so we're trying to prove something about this function f, which is defined as in problem 2-4. So we should recall that, what that means. So recall that we have this function g. What happened? What is this? How? Recall that g is continuous on the unit circle so it's g from R2 to R, and it's continuous on the unit circle. G01 equals G10 equals 0, and g of minus x as a vector. Here, I'll write v for vector, just so that we know that these are vectors and not points in R. Is our vectors v in R2. Okay. So that's a g is just some continuous function which satisfies these properties. Then f is given by f of x equals norm of x times g of x over the norm of x. If x is not equal to 0, here of course x is a vector, and f of the vector 0 is 0. So f goes from R2 to R as well. Okay. So, we want to show that dx f of 0, 0 exists for all x. Okay, so if x is the 0 vector, then you know what I'm going to do? I'm going to just use vector notation. Okay, I'm starting to regret this decision. No, it's fine. So if x is the 0 vector, then dx f of 0 is going to be 0, so it exists. If x is not the 0 vector, then dx f at 0 is going to be, by definition, the limit as t goes to 0 of 1 over t times f of t times x minus f of 0. So this is the limit as t goes to 0. We still have 1 over t. Now we have, okay, so f of t times x. We're taking the limit as t goes to 0, so t is not equal to 0, and the vector x is not 0. So we can use our formula for f at non-zero values. So it's norm of t times x times g of tx over the norm of tx. And then we're subtracting f of 0, but that's 0. We know that. Okay, so now this is the limit as t goes to 0. We can pull out the norm of t out of this norm of t times x, and so we get the norm of t divided by t. So if t is positive, then the norm of t divided by t is going to be 1. And if t is negative, then the norm of t divided by t is going to be minus 1. So here, actually, let's write it out in stages. Actually, no, let's not do that because I don't feel like it. So it's just going to be the sine of t. So it's going to be a 1 if t is positive and a 0 if t is negative. And of course, it's going to be 1 if t is 0. Oh, but that's not even something we have to consider at all. Okay, so we have this, and then we multiply times g of, and then we've also got t over the norm of t, so that's going to be sine t of t again. We're multiplying by x over the norm of x. Okay, but look at this. So let's suppose that if t is positive, then sine of t is going to be positive, and this just reduces to g of x over the norm of x. If t is negative, then we're going to have a negative out front and a negative within the argument of g. It's going to be g of negative x over norm of x. But we know by the properties of g that if we have a negative on the inside, we can pull it outside. So in this case, so we can pull that negative sign outside, and so we get two negative sides on the outside. So it's negative g of x over the norm of x. But the negatives canceled, so we just get g of x over the norm of x. So we get the same thing regardless of whether t is positive or negative. And we get something which no longer depends on t, and so we can drop the limit as t goes to 0. So we just end up with g of x over the norm of x, which exists, obviously, because g is defined at this point, since if x is a non-zero vector, x over the norm of x is going to be a vector of norm 1, and so this vector lies in the domain on which g is defined. And so this exists, and so dx f of 0 exists. So we've proven that for all x, dx f of 0 exists. Okay, so now let's do the next part. So now suppose g is not equal to 0, then there exists some point xy such that gxy is not equal to 0, clearly. Wait, nope. No, I was right. Gxy is not equal to 0. Then dxy f at 0 is, as we have just proven, okay, so we know that, well, xy cannot be the 0 vector because it has to lie in the unit circle. So we can use our formula. This is going to be g of xy over the norm of xy. But we know that xy is in the domain of g, and so it must lie in the unit circle, and so its norm must be 1. So this denominator here must be exactly 1. So this is just g of xy, and as we have proven, this is, or as we have assumed, this is not equal to 0. However, let's look at the individual coordinates separately. dx0, f at 0, is going to be g of x0 over the norm of x0. And so this is just going to be the vector 1, 0. So this is g of 1, 0, and we know by the definition of g that this is 0. And d0y of f at 0, same thing. It's going to equal g of 0, 1, which is equal to 0. So d x0 plus 0y f at 0 equals dxy f at 0, which is not equal to 0, which is in fact equal to dx0 f0 plus d0y f0. Okay, so that's the second part. And yeah, that's all that we needed to prove in this exercise. And so let's see here. What's the thing that's weird here? So we have that the derivative exists for all x, but we can't do this this summation thing. And so I think that goes back to I'd have to go back and check, but I think it goes back to the there's some other condition that you need in order to do this summation thing. In order for it to be true that dx plus yf is equal to dxf plus dyf. I think it's a continuity thing, like maybe continuity of the derivative. But basically, this is supposed to show an example where you can define the derivative at the origin, but the summation thing, and you can take the directional derivative in a direction, but you can't do the summation thing. And so that's really the point of this exercise, and now we're done.